Okay, so now I'm going to go through the possible poker hands and all the different combinations of them. So, supposing that we have the suits, and this is going to be generalized, so it doesn't just apply to poker, it would apply to any number of suits and with any number of cards. So suppose our suits are labeled A through Z, and in each suit the card numbers that are available are 1 to N. And so in general we could have any card like let's say 5C or 31F. These would all be cards where F would be the suit and 31 would be the number of the card in that suit. And in general there don't have to be just 26 suits. The A through Z really represents like any number of suits. So if we want to write down all the possible combinations of we want to have two cards in our hand, and so we want to figure out all the possible combinations of two cards. So what we can do is we can write down 1 through N, 1 through N, and we keep doing this. And we consider that these cards are from suit A, and these are from suit B, and then these will be from the final suit. And then we go here and we can do the same thing. And again, these are from A, from B, and from the final suit. Now, because we have two cards in our hand, it doesn't actually matter which order we get the cards in. So say we have a hand with two cards, one of them would be this and another one could be this. This is our hand. Our hand contains these two cards. Now this is equivalent to having this hand. It makes no difference which order we got the cards in. And so we're not going to count these as two different hands. We're going to consider our hand as being just a set containing these two cards. And therefore, when we're looking here, we will only look at the upper diagonal part of the matrix that we're considering. And hopefully that should be obvious in a moment what I mean by that. So if we try to break this up into a grid, this will be effectively our matrix of the possible hands. And when I say we consider the upper diagonal, that means that we'll only consider cards in this part of the matrix, but not down here. And in fact, you can't even have cards on the diagonal. So you cannot have a hand that contains the cards like 1A, 1A, because these are both the same card. And we have a deck of cards and there's only one copy of each card. So this is not a valid hand, which means that cards on the diagonal, so here we'd have 1A, 1A, or somewhere here might be like 5B, 5B. These are not valid combinations. And so we draw a line, we draw a line like this, going down, sort of cutting off, and we just effectively keep doing this. And the detail, if you get the idea, the drawing doesn't need to be too accurate. So we have this line that cuts everything off, and down here, this stuff, we don't worry about this. These combinations are not going to be considered because they're just either not possible or they're copies of combinations that will be appearing in this region. So we can just scribble this area out and not worry about it. Now, the first combination we could consider would be 1A, 1B, it would be 1A, 2A. So in this region here, in this little square, all the cards are from A. And so again, we can actually divide something like this. And then we can go like this. And we can split the board into regions. And these lines just keep going down. We go across like this. And what you will find is that regions like this one, and this one, and this one, and this one, these are all regions where we have cards of matching suits. Okay, so we have both the cards in this region will be from B. So the suit will be the same, or here the suit will be A, here the suit will be something else, and here they would both be from suit Z. Now cards in all the other regions are not matching, so they're from different suits. However, they may have matching numbers, so you could have a 1 and a 1, like 1A and 1B could be here. So what we do is we break the cards up into these grids, and then the next thing that we're going to want to consider will be inside each grid what kind of, well, how many combinations, like how many ways are there to get that value in the grid. And because of the way we've constructed the grid, there's actually just one, for each cell in this grid, there's one way of doing it. So there's one way of getting 1A, 2A, there's one way of getting 1A, 3A, and there's one way. So for every single one of these, there's just like one combination that would get you the right answer, or would get you that hand. So we can just consider that they're all ones. And now, because we don't really care about the specifics of the suit, like, so say if it's 1A and 1B, or if it's 1A and 1C, as long as the suits are not matching, we don't really care specifically which suits they are, we just care about the fact that they were not matching. So we want to get our suits, we want to know how many matching suits we have and how many not matching suits we have. And so first of all, let's consider the non-matching suits. So this here, what I'm drawing, is effectively taking one of these squares out from here. And so we have a suit here, say A and B, but these could be any two different suits, distinct suits. And in this square, on the diagonal, the elements will be matching numbers. So here we've got the numbers 1 through n and 1 through n. And so there's one combination that gets us this, there's one that gets this, and we have all these ones as we've seen, and the whole thing is filled up with these. So in this case, it's effectively n is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So if n is 7, this is what our little grid between A and B would look like. Now, as we said earlier, we don't really care which order the cards are in. So if we have something like A2, B3, we don't really care if it's A2, B3 or if it was B2, A3, because the numbers are really the main thing that we care about, and then we just care if the suits are matching or not. And so what we can do is we can add or simplify or change our diagram a bit. And so now everything that was on this lower portion, we actually will just copy it and add it over to the corresponding location. So say here we have AN B1. Well, now we're going to add that to A1 BN. So this would become a 2. And so what will happen is everything on the diagonal will remain a 1. And then everything else will become a 2. And then here now we've added all of these over there. So these are now empty and we just have this upper triangular matrix. And so now that we've done that, we can consider all of these. So this one, this one, this one, this one, this one. These are all in that format where we know that the number of like one pairs is 1, the number of 1 2 pairs is 2, the number of 1 3 pairs is 2, the number of 1 4, and so on. And that means that we're now like not really worrying about which particular suit they came from. And so what we want to do is we want to now add up all of these on top of each other, because as we said, we don't care about the suit, so we can just add these on top. So what we need to know is how many of these squares there are. In this case, there's 1 2 3 4 5 6, but in general, how many would there be if we've gone from A through to Z? And the answer to that is that we have Z minus 1, or the numbers, so say Z is the 26th suit, then but in general it could be any number suit, and we'll just denote that with Z like this. So we have Z minus 1 possibilities from this row, and then we have Z minus 2 from this row, and we keep going until we get all the way to 0. So this is, if we sum all these up, this is the sum up to Z minus 1 of this, which is equal to Z minus 1 over 2. And that is the number of ways that we can have these grids. And so we're going to add up effectively this grid this number of times. And so these numbers are all multiplied by this number. And that will give us the number of non-matching suit pairs. So supposing that this game is poker, then there are 4 different possible suits. And therefore, and there are also 13 different cards. And so here we would have this number would become 4 times 3 divided by 2, which is 6. And so here, instead of 1, we would have 6, and instead of 2, we would have 12. And on this diagonal, it's all going to be 6s. And on these, it's going to be 12s. And then we want to consider, we've considered all of these. So now we have to consider these regions. And these are the regions where they are from the same suit. And each of these regions actually fits perfectly into this blank space that we now have here. And so if we forget about this upper half for now, and we think for each of the lower regions that we had, so for each of these we just have one copy of every pair. Now we want to know how many of these regions we have, and the answer to that is that we just have 1, 2, ... up to Z. So we are going to have this many copies of this bottom half. And I hope that that's clear, because it's just from the diagonal across here, and the length of this diagonal is just the length of the number of columns, and that's going to be like 1, 2, ... up to this number. So we want to take the lower half and multiply it by this value, and if it's poker, this value is equal to 4. So then in the lower half we now have 4s, and these are the offsuit pairs, and so on. And so this is the number of, say, this is the number of 1-1 pairs, and obviously a 1-1 pair, they cannot be from the same suit. Then say this is the number of 2-4 pairs. Now 2-4 pairs, and this is the number of 2-4 pairs from distinct suits. So this could be like 2 of clubs and the 4 of spades, or it could be 2 of hearts and 4 of diamonds, or anything. And there are 12 possibilities here. And also, in these 12 possibilities, we've counted 2 clubs, 4 spades as being different from 2 spades and 4 of clubs. Because in terms of the number of ways you can get it, it does actually add up to be necessary to do that. And then in the lower region here, something like this one, this is the number of 2-4 pairs where they're from the same suit. So this could be like 2 of spades and 4 of spades, or it could be 2 hearts, 4 hearts, or it could be 2 diamonds, 4 of diamonds, or it could be 2 of clubs, 4 of clubs. And in this case, if we try to switch the order around, we would actually still end up with 2 of spades and 4 of spades, so we wouldn't get anything different. And that's why in this case the order doesn't matter, and there's just 4 combinations. Well, when I say the order doesn't matter, what I mean is when you switch the order, you don't get anything different. So this is how this is all worked out. And what you might notice is that this 12 here is actually can be thought of as like you have 4 choices for the first card, and then you have 3 choices for the second card, and that's 12 different combinations. And then this 6 number here, this can be thought of as we have 4 cards or 4 different possibilities for the suits, and we have to pick 2 distinct versions of them, and the ordering that we pick doesn't actually matter, and that will be 6. And actually you can think of this as doing this process, but then noting that the ordering does matter, and therefore you need to multiply by 2 factorial, and you would get 12 again. And then this 4 finally is just that we have the freedom to choose the first card. So we have 4 choose 1 choices, but then the second card has to be from the same suit. So now we have no more choices, so we get 4 there. And so that is how you can get the poker hand matrix.